All right, so before we do something new, I just wanted to have a quick conversation about what you found out in your group. So starting with Group A, in your matrices here, can I ask which one of these three matrices, if any, involved a reflection of some kind?
Reflection?
Reflection. Did you see any reflections?
No.
Didn't see any reflections. Did you say that any of them involved a shear of some kind?
Mm-hmm.
Which ones?
A and B.
A and B. So you saw a shear here and a shear there. Okay. Shear. What about C?
Projection.
So C, you saw projection. Okay, so let me just focus on the projection for a moment and go to the other group, Group B. So of the matrices that you had, here are Group B's matrices, which one of those three matrices did you say had a projection?
B.
B. So matrix B was 2, 1, 2, 1, read across the rows. The other group's matrix, can you give us what your projection matrix was in your group again?
1, 2, 2, 4.
1, 2, 2, 4, like this. So tell me, what do those two matrices have in common that's making them projections? So you correctly identified both of these as projections. But why? What's true about both of these matrices?
Same slope.
What have the same slope?
Vectors.
The vectors, and where do we get the vectors out of this matrix?
Out of this one?
Well, really either, right?
Yeah, well, 2, 2, and...
Right, let's take a look at the columns. The columns of the matrix on the left are both vectors that have a slope. What's the slope of these two vectors on the left? 2, 2, and 1, 1. Yeah, the y component divided by the x component gives me. Both of those have a slope of 1. So what's the relationship between those two vectors? What would we say? Using the language we've developed in the past couple of classes. What's the algebraic relationship between the two? If this first column is v and the second column is w, then how are v and w related? They're multiples of each other. Specifically, v is equal to 2 times w here. And actually that same relationship, very same relationship, holds for the second matrix. V is equal to 2 times w. And the first column is twice the second column. So we know that they're multiples of one another. That also means that they are geometrically parallel one to another. That also means, what else about these two vectors?
They have one solution. Oh, wait.
Solution to what is the question?
Well, if there was like a linear equation, they would have, since they're on top of each other, that is that they...
Since they're on top of each other, that means something about the nature of solutions to ax equals b, right? For these matrices, A and B. And that's actually where I want to pick up the story that we left off here. That either of these two matrices, if we look at the solutions to ax equals b for them, we're going to find out something about the nature of those solutions. So here's a picture of that transformation, 1, 2, 2, 4. And if I choose a bunch of different input vectors, a bunch of different purple vectors to plug into my linear transformation, and I move them around, how are their images related one to another in the codomain? It stretches or reflects. So that's how they're all different from one another. How are they all the same? They lie on the same line. The images of all vectors lie on that same line. In particular, if I choose the vector 1, 0 in my domain, what's the image of 1, 0 in my domain? Sorry, the image of 1, 0 as an element of the codomain. 1, 2. And where is 1, 2? It's the first column of our matrix. After all, that's how you build a standard matrix. You take the standard basis vectors, the first of which is 1, 0, in this case, and you just transform it, and its image becomes the first column of the standard matrix for this transformation. Likewise, if I adjust this to be the second standard basis vector, namely 0, 1, 0, 1, there we go, then the image of 0, 1 in the codomain is 2, 4, which again, that's the second column of our standard matrix, because it's the image of the second standard basis vector, 0, 1, under this transformation. But, notably, those two images lie on the same line, as Jocelyn says. 1, 2 is right there, and 2, 4 is out here. And so because of linearity, as long as the image of 1, 0 and 0, 1 lie on the same line, then the image of any linear combination of 1, 0 and 0, 1 will also lie on a linear combination of 1, 2 and 2, 4. But when I take all the linear combinations of 1, 2 and 2, 4, I'm not going to get very many different places. I'm only just going to get to places on that line. Right? So that's the reason that we can call this a projection, is that really the entirety of this two-dimensional region on the left, the domain, is getting all compressed onto that line in the codomain. And if we illuminate this picture with some additional labels here, that line that all the images lie on is called the column space of this matrix. And it's defined, this is where I say we're sort of talking about some material from chapter 2 at the same time here, that the column space is defined as the set of all linear combinations of the columns of our matrix. In other words, it's the span of the set of vectors which are the columns of the matrix A. And again, the role that it plays is it just tells us when I multiply A, the matrix, by anything X in the domain, I am guaranteed to get something which is on this column space in the codomain. So every image of every vector from the domain is going to lie somewhere, in this example, along that line. And that line is a line precisely because it is the set of all linear combinations of the first column and the second column of this matrix. But because that first column and that second column are parallel one to another, their linear combinations can only take us to points on that line and can't take us to any point off that line. And then the next observation to make about this was your point about the nature of solutions to this system of equations. So let's pick on one particular B vector in the codomain. Let's pick on B equals, 2, 4. So I'm just going to slide this. By the way, notice that if I'm picking a B that's not in the column space, what is my solution set? What purple vectors are landing on this green vector? At least according to the applet. If I'm trying to solve AX equals B for the vector B equals, 4, 3, then what is my solution? There's no solution. Because the column space consists of all the B's for which AX equals B is consistent. It's another way to think about what the column space is. AX equals B is consistent only for these B's. For B's that are in the column space. Only if B is in the column space. And so in the example that's on the screen right now, we chose a B that wasn't in the column space, and therefore we cannot find an X such that AX is equal to that B. So the solution space, solution set for A times X equals 4, 3 has no solution. is an empty set. AX equals 4, 3 has no solution. Is inconsistent, in other words. Because 4, 3 does not belong to the column space of A. Because the column space is just that line. Okay, but what if we choose a B that is in the column space? Then what is the nature of the set of solutions of this particular system? So let's adjust this so that we're at, I don't know, 2, 4. 2, 4, there we go. Now the system of equations, or the vector equation, I guess, AX is equal to 2, 4. How many solutions does it have? Well, at the very least, the app has found us one. Here's one. -5 halves, comma 9 fourths is a solution. So because this was in the column space, because 2, 4 was in the column space, that made this a consistent system. In other words, we had a solution. And so now the question is, how many solutions do we have? Well, we definitely have this one, -5 halves, comma 9 fourths. How do I find others? Does anyone else see a very simple solution to this system of equations? What vector, which when we multiply it by this matrix, definitely gives us 2, 4? So -5 halves, 9 fourths. That was the solution. But so too is the vector 0, 1. Try it. Because if I multiply this matrix here by 0, 1, I get the linear combination 0 times the first column plus 1 times the second column. And that's exactly just the second column of the matrix, which happens to be 2, 4. So 0, 1 is also a solution. So is the solution to this system unique? No, we have more than one. And therefore, if it's not unique, the solution set must be infinite. We must have infinitely many different solutions. And if we were to find the parametric vector form of the solution set of this, we would get the entire bold purple dotted line on the image on the left. So the solution set, every point along this line here would be a part of the solution set. So 0, 1 is in there, so is -2.5, comma 2.25, so are infinitely many other things. So because this matrix happens to have that projection aspect to it, that also means that there are infinitely many different points whose images all land on the same place, in this example, 2, 4. So pictorially, it's as though this entire line, when we apply this linear transformation to it, is all getting squished onto that single point in the codomain. Does that kind of help to illuminate the geometry of what's going on here? That what's being squished in this projection is that that entire line is being squished. And that entire line is being squished onto the point 2, 4 precisely because there is an entire line of things which is all squished onto the origin. That's the lighter purple dotted line on the left, called the null space. But the null space of a transformation is everything that gets squished onto the origin. And it just so happens that the solution set and the null space look an awful lot like one another. This is what your group discovered a couple of days ago. That when you look at the parametric vector form of solutions of AX equals B, that would be the solution set up here. Solutions to AX equals B was this line. Versus the solution set of the homogeneous equation AX equals 0. That's the null space. That those two sets are parallel to one another. So in this example, since one of them is a straight line, The other one is also a straight line, just moved a little bit. So just knowing that this linear transformation is a projection, we get a lot of mileage out of that. The reason it's a projection is because its column space is just a straight line. It's not the entirety of the xy plane. And because it's just a straight line, because the two columns of this matrix are parallel. In other words, they're linearly dependent on one another. So because the columns are linearly dependent, the column space is not the entirety of the xy plane. In this example, it's just a line. And because of that, we also know that solutions to the equation ax equals b, when they exist, and they only exist when b is in the column space, but when they exist, the solutions are also not unique. And so what your groups are going to do now for the remainder of our time today is figure out what is it that this matrix can tell us, right? The matrix of any linear transformation can tell us about these properties, the uniqueness versus not uniqueness of solutions versus the consistency or inconsistency of a system of equations. And when we do, we're going to be reframing those properties in terms of familiar language about functions, because when we're talking about linear transformations, we're talking about functions. And the question of uniqueness of solutions is going to be answered by the question whether that linear transformation is one-to-one or not. And the consistency or inconsistency of these equations are going to be determined by whether or not the relevant linear transformation is onto. So in your groups, you're going to answer whether or not, or first of all, how to tell whether a linear transformation is one-to-one and onto. And then you'll look back at the matrices from part A, and actually number 2. We'll also look at the matrix from number 2, and tell me whether or not those are one-to-one or onto based on their matrices.